Hello everyone. Today I'm going to introduce complex valued neural networks for privacy protection. Previous studies have found that adversary attackers can extract input information from intermediate layer features. In this paper, we study the possibility of boosting the difficulty of such attack. Therefore, we propose a set of rules to transform traditional neural networks to complex-valued neural networks. Intermediate layer features in your networks are complex-valued, but all parameters of complex-valued neural networks are still real numbers. Our basic idea is to hide the input information into a randomly selected phase of complex-valued features. The target phase can be considered as the key for the encryption. Without the target phase, the attacker cannot extract the original input information, even if the attacker can get the intermediate layer feature and parameters of the neural network. As for the user with the target phase, they can easily decrypt the feature and recover the output from the encrypted features. Here, we provide a more detailed architecture of the complex-valued neural network. The network consists of three modules, including an encoder module, a processing module, and a decoder module. The encoder extracts intermediate layer features from inputs and turns a real-valued feature into a complex-valued feature. Then, the encoder encrypts the complex-valued feature by hiding the input information in a specific phase. The encrypted complex-valued feature will be sent to the processing module. The processing module further processes the feature without changing the phase that hides the input information. The decoder decrypts the processed feature back to a real-valued feature and gets the final result. The encoder and the decoder are embedded inside a local device, and the processing module is located at the public computation center. In order to enable successful encryption and decryption, the processing module needs to satisfy the rotation equivalence property. We propose a set of generic rules to revise the operation of each layer in the processing module to ensure the rotation equivalence property. For example, for the convolutional layer, we remove the bias term. For dropout layers, we randomly drop out both the real and imaginary parts of complex-valued features to ensure the rotation equivalence property. Please see our paper for more discussions about the revision of each layer. In this way, the rotation equivalence property of the processing module can be recursively guaranteed. In order to further boost the difficulty of hacking the input information, we use adversarial learning to train the encoder. An ideal encoder requires the encrypted feature contains sufficient information to cause obfuscation with the real feature. Besides, the encrypted feature and the real feature follow the same distribution, so that it is hard to distinguish which one is the real one. That is, attackers cannot distinguish which phase contains the input information. The overall loss of learning is formulated as follows, which contains the adversarial loss and a loss for the target task. In experiments, we designed two types of attacks to test our method. First, we used intermediate layer features to reconstruct the original input, that is, the feature inversion attack. Besides the complex-valued neural network, we designed the following three baselines for compression. Note that we also divided the baseline neural network into the encoder module, the processing module, and the decoder module, which was same as the complex-valued neural network. The first baseline was the original neural network without any revisions. The second baseline was the neural network with noises. We injected noise right after the encoder module, and the noisy feature was fed into the processing module. The third baseline was the network with additional layers. Since the encoder of complex-valued neural network is based on generative adversarial network, we designed a baseline with the same structure of the complex-valued neural network for fair compression. Here, we visualize reconstruction results of different networks. The last two rows, that is, images within the red box, are images reconstructed by features of complex-valued neural networks. In the last row of syllabi, we cannot identify the person in the reconstructed images. Compared with reconstructed images of other baselines, attackers cannot effectively reconstruct inputs using features from complex-valued neural networks. Here, we provide more quantification results of feature inversion attack. We find that complex-valued neural networks have similar performance as traditional DNNs, but exhibit better performance in privacy protection. Furthermore, we tested the failure rate of reconstructed images from different networks. We have 5 human annotators to recognize the object in a group of reconstructed images. The results show that most annotators fail to recognize the reconstruction from the complex-valued neural networks, which demonstrated the privacy performance of our network outperformed other baselines in the feature inversion attack. Another type of attacks is the property inference attack. As the figure shows, the property inference attack uses intermediate layer features to infer some sensitive input properties. For example, if we train a neural network for the age recognition task, attackers can extract intermediate layer features and train another network to infer other provide properties, such as the gender. We designed various types of property inference attacks. Curves in this figure provide the inference performance of different types of inference attacks. We observed that the error rate of the inference attack on the complex-valued neural networks was significantly higher than other baselines, and was close to the random selection. Here, we provide more quantification results. We found that error rates of inference attack on complex-valued neural networks were close to random selection on the CIFAR 100 dataset. Thus, complex-valued neural networks diminished the attacker's power in inferring input-sensitive properties and outperformed the baseline network. In conclusion, we propose a generic method to revise traditional neural networks into complex-valued neural networks for privacy protection. The input information can be hidden in a random phase of complex-valued features. Experiments show that complex-valued neural networks can effectively boost the difficulty of hacking input information. Please read our paper for more details. Thank you.